So in this, we will delve into the innovative and fascinating world of the underwater, the depth of the seas. And it's a unique environment where we have several challenges due to the variable lighting conditions, the temperature, pressure, turbidity, and of course, for that, we need much more innovative approaches and solutions. And for this, our first speaker is Professor Gianluca Antonelli from the University of Cassino and Southern Lazio, Italy. And he will talk about distributed underwater bearing only multi-robot acoustic source position velocity estimation with latency and packet loss.
Okay, good afternoon, everybody. Thank you for the presentation, and sorry for the very long title. This will be a quite technical presentation with respect to the previous one, so I do apologize, because also after lunch, I mean, it's difficult, and also there are some equations, so I just prevent you. Now, what is ISME? I'm a full professor in a public Italian university, but we work in this topic together with an inter-university center. The name is ISME. And it has been funded more than 20 years ago by the University of Genova and Pisa, and then enlarged up to 9 universities. I belong to the University of Cassino. So I assume that, I mean, you all know where Italy is, but some of the universities belonging to the center were quite small, in small villages, so maybe you don't know. Cassino is there. Is in the middle between Roma and Napoli, where I come from, basically, actually. And all the other universities are the one involved in this center. So, as I said, the center has been established more than 20 years ago. We don't have public funding. We are a public Italian university. So all the research that we do is with participation to the competitive calls, like FP7, H2020, Horizon Europe. Those are basically our main source of fundings, together with all the national calls, and our relationship with the Italian Navy. And this is what I'm going to talk with, to you today, about one activity that is ahead of a wider activity with the Italian Navy. Our background is basically automatic control. I mean, the majority of the team, as myself, we do have a background on automatic control, but we cover from, I mean, applied mechanics, artificial intelligence, acoustics, a little bit several aspects, vision, several aspects of marine technology, okay? We do have an agreement with the Italian Navy and a joint laboratory. The name is C-Lab. In Italian is Sistemi Eterogenei Autonomi, is Autonomous Heterogeneous Systems. Okay, the acronym is C, which is very nice. And the dock over there, this is located in Spezia, in the northwest of Italy. And the dock here is just side by side of the NATO Underwater Research Center. The name is CMRE, so they're very in the same area, let me say, with the same entrance, basically. Okay, let me focus on the multi-robot topic we are talking today. This is just a bird's-eye view of all the logos, all the projects funded in the last 10, 15 years, which is the most exciting part of having a project, is to design the logo. And I will focus on the few of them, more recent one, related with the topic of today. So first of all, let me just show you a small video of We Must. This was a project led by Professor Indiveri, Giovanni Indiveri from the University of Genova, and we were involved in this as a Cassino. The topic of this one was geophysical and geotechnical survey. I will run the video as I'm going to talk. It was, let me say, the start of the activity of multi-robot system I'm going to talk today a little bit. So basically, the geotechnical, geophysical survey are run with thousands of microphones physically related to one each other in a huge, I said, carpet of hydrophones. It's hundreds of meters wide by hundreds of meters length, up to even 1 kilometer. And the idea of the project was to remove this physical connection and to have the hydrophones mounted on autonomous vehicle. And the vehicles, in order to have good data to work with, should have been strictly coordinated among them, localized and able to communicate among them. So basically, the project was a 3-year project whose objective was to come up with a mock-up, so with a successful demo, which has been done in, we were in Portugal here with our, Portuguese colleagues hosting us for all the experimental parties. Sines is an industrial harbor in the south of Portugal. And the final video is quite nice. We do have 2 catamarans, autonomous. Each of the 2 catamarans is carrying an acoustic source. And the acoustic source is needed because the hydrophone read the reflection of the acoustic wave and are able to make the characterization of the sub-bottom profile. And then we do have several vehicles. Some of them, the surface one, are used to localize the underwater one. And the underwater one are equipped with atomic clock in order to have a really accurate position. This was strictly needed by the acoustic team, which was in charge of post-processing of the data. So this is one. The first, let me say, big project on multi underwater vehicle. Then another one, and this is related to the topic I'm going to talk today, is funded by the Italian Navy. Basically, the objective is very, let me say, simple. I want to localize the source of a noise. Okay, this is a possible threat. And the only way to understand that it's coming is to hear for the noise, okay? So the idea is to have, hydrophone, of course, but multiple of them mounted on moving sensors. Now, it's very simple from the geometrical aspect. Now, what is the issue? The issue is that I can hear the noise up to 50 kilometers, but the thread is moving, and it can move up to 20 meters seconds. And since the acoustic wave travels at 1500 meters seconds in water, it means that I hear the noise after more than 30 seconds. And the target already traveled up to 500 meters in a direction that I don't know. So the problem is not, yes, it's coming from that direction. The problem is to know as much precisely as possible the position of the threat. This is just a picture of the vehicle. So we are going to the water next month. So it's an ongoing project. I will give some details very soon. We do also have 3 national projects, smaller one, on multi-robot teams. And one is my university is involved in 2 of those 3 with the other universities of the center. Those are very small projects funded by the Italian National Ministry of the university. Okay, so I switched to LaTeX, so let me forgive for this old style presentation if I found the PDF reader. Yes. Okay, sorry, I switched to LaTeX. This is the same as earlier. Now, the problem is, as I said, is very easy. Because if I have 3 vehicles, and each of the vehicles can hear the noise and can measure direction of arrival, this is an intersection of lines and a problem that the students solved at high school, so 15 years problem. Well, yes, this is true, but the problem, as I said, is the accuracy. So let us see, and this will be used as benchmark. Okay, I don't care about the speed of water the speed of the sound in the water. I just take the measurement and intersect with my neighbors, and this for me will be the benchmark to improve. Okay, so the problem is localize a moving target. I do have some slowly moving vehicles. The vehicles carrying the hydrophone moves at a speed of 1 knot, more or less, so they're very, very slow. They can measure the direction of arrival, but and also the intensity, but the intensity is not useful because for several reasons, this is not calibrated and cannot give us the information of the distance. Otherwise, we don't need anything else. Now, the acoustics. The acoustics underwater, in this case, is used as information carrier because it's the noise I want to localize, but it's also used for underwater localization and communication. So basically, the problem is that I need to take into account the propagation delay of the acoustic surge, and I need to take into account also the communication latency among the vehicles, the very small bandwidth. They cannot exchange a lot of information. They can exchange very small packets, and within a TDMA protocol, we'll see. Then underwater, the packets get very often lost, and they can have multiple paths. So basically, what happens underwater is sometimes I receive the data from another vehicles, even in a not casual manner. So I can have a packet sent earlier. And so the sampling is obviously not uniform. So basically, if this is the target, as T0, it makes noise. This is one possible sensor. It receives this measurement here in T1. While another sensor received in T2, of course this is not in scale. And this line is what they receive, but basically this is receiving this line here, and this is receiving this line here. So the intersection is made, the naive solution is clearly affected by a certain larger error. Okay, why do I need multiple sensors? Can I just have one moving sensor? In theory, yes. Mathematically, yes. But the sensor should be much faster than the target, which is not the case. In practice, underwater, this is what happened. The sensor has a lot of measurement, a lot of data, very similar one each other. So it's trying to solve a badly balanced numerical problem. So I need to have multiple sensors. I cannot solve it with one single hydrophone. Can I implement recursive algorithms, stochastic or deterministic? Maybe, but it's very hard because the sampling time of the data is not constant. So the tuning of the gains is very, very hard. So we discarded all this kind of recursive approach. Few details about the communication. We do have a TDMA protocol. So there is a window which is related to the number of vehicles. We will see with 6 vehicles. And in each of these, and so the time windows is divided by the number of vehicles, and each time slot, each vehicle can communicate and then listen for all the remaining time. Then we implemented the packet delivery ratio given by the group from Rome that is expert in acoustic communication, which represent the probability that that packet is delivered to another vehicle, and this is related to the configuration, to the distance of the vehicle. It's a data that in our case is more or less from 80% to 95% of the packets targets are received with a latency up to 10 seconds. So I do have the data with a lot of delay, even, both for the propagation delay and for the latency of the communication. I need to face this problem. So I apologize, there are some equations, so just to give you the idea, but I will go very, very quickly on the equation. And I asked for permission, and they told me that it's still allowed to put some equations in the presentation. So I do have my unknown, which is the position and the velocity of the target, okay? And my measurement is an angle, is the direction of arrival. The issue, so it is this beta here. So the issue is, okay, I just have an inverse tangent for quadrants, and then this is the position of the target, but there is the propagation delay, which is also known, okay? With a certain noise, okay, it's not Gaussian, the noise, the team in charge of developing the sensor, they told us, no, it's a PDF, a uniform probability density function. Okay. The problem is that the delay, the propagation delay, is known only when I hear the noise. So it's not known in advance, of course. Okay. This is the measurement. We can rewrite a little bit our equations, and this is known since this is 1979 here, so since 20 years. And we can have at the left-hand side some known quantities. The right-hand side, still we have the unknown, more or less mixed, and the new noise, which is now a distance, is not anymore an angle. Okay, so let us try to have a linear algebra, a regressor. So one single measurement, one line. This is a scalar. This is a y/2 vector, known, okay? This is a strange unknown because I do have the unknowns here, but also for every measurement I have one new unknown, which is the propagation delay. And so, yes, it seems to be a linear algebra, but not yet. Okay, I ignore this problem for the moment, and I say, okay, if the velocity of the target is constant, which is a basic assumption, if it's not constant, I cannot do anything, so it has to be constant, I can measure a posteriori the propagation delay, okay? Okay, I take this information for good. And what I do is, I project all the unknowns, I collect all the measurement, so P measurement, all those are unknowns, so this vector is plenty of unknowns. Okay, let me project everything to the current temporary time, and in this way, I got something that is close to linear algebra. So y is equal a multiplied by these 4x1 unknowns, but a now is orange. Why it is orange? Because I hidden the dust under the carpet, because here is plenty of unknowns. All the propagation delay are in the regressor, which is unpleasant. Okay, let's see if I knew A, this is linear algebra, so pseudo-inverse. It's first year of engineering university. Okay, what is the idea? It's very simple. Okay, let us ignore the propagation delay for the first estimate. And then we use the first estimate to estimate all the propagation delay. We put it inside the equation, and then we continue recursively until the error decreases. And we stop when the measurement noise tells us to stop. Okay? So this is basically the idea. We do have to make some consideration about the quality of the noise and the data, because, okay, our problem is a very simple one. However, we face two problems. One is that the noise is not the same for all the measurement, and the other is that I have to pay a lot of attention in the quality of the data that I'm collecting. So very simply, skip this one, very simply, well, the noise is not constant. It is constant in the duration measurement angle, but now I transform it in distance, so basically, clearly the noise is larger when the target target is far away. And in the first estimate, I don't have this information, but then in the following one, I need to take this into account. So the quality of the data is not the same for all the line of the regressor. And then my regressor looks like something like that. I'm the generic vehicle, and most of my data are colored in blue. So most of the data are taken from my own sensor. And then I have a data from another sensor, a couple of data for another one. So basically, if I just make the minimization of the least square, I tend to polarize the estimate towards the measurement coming from my sensor. It's something that is not difficult to take into account, but it needs to be taken into account, the two issues, with the data and with the noise. Again, since I have a pseudo-linear formulation, something close to linear algebra, I can optimize. Obviously, this is a post-processing optimization, because I don't know where the target is coming from. But if I knew, well, with two sensors, the blue dot are the sensor, the best position for the unknown target, which is a thread, so it's only hypothetical, of course, is when it makes a 90 degrees angle with the two sensors. It maximizes the metrics related to the numerical balance of the regressor, okay? With three is something like that. Again, I don't know in advance where the thread is coming from, so this is theoretical. But it gives us the side information that I don't have to cluster all the sensor in one place. I need to spread my sensor as much as possible, and I can also make some optimization based on some hypothetical directional arrival of the thread. So if I have some direction that are preferred with respect to the other, I can put my vehicles in a configuration which maximizes the quality of the data, okay? And since everything is very slow, so we will see, so 2 meter-seconds, I need to collect a lot of data. It means that several minutes elapsed since the first measurement and my estimate. I can also ask the vehicle to move in a way to optimize the following data, okay? And this is something I'm going to work, not going to present today. Okay, it is, it is true that with a good numerical balance, I got a smaller error. Well, we made simulation, yes, we have confirmation, numerical confirmation of what the theory tells us, likely. And then I just have some numerical simulation. So we spent some effort in having a good communication simulation, and also we simulated the wave propagation. So it's just a first order dynamics for the wave propagation in order to have really, the propagation delay. So 6 vehicles, each vehicle can communicate for 3 seconds. It means that they have a TDMA of 18 seconds. I want each regressor to have 50 lines. It means that I have to wait for a lot of time until I can have the first estimate. So basically, show you. So basically, with the PDM, so 85% of the data are lost. Those are the sensors, those are the measurements. This is my thread that is coming, is 10 kilometers away. I don't have the estimate until I have enough data. They are communicating with each other. And now I have the benchmark, so the next solution in gray, and the proposed solution in green. Well, the error is 0. Yes, because here we are simulated without measurement error. So basically, this is a debug, so it works, but also the algorithm hasn't been mathematically proven, so it's also a confirmation that it's okay. The iterative way can be used. So here a lot of just confusing plots, but the only important is here, the percentage error. The next solution has between 10 and Cassino, as I say, without measurement noise. It means that there are no bugs in the code and that, okay, the algorithm seems to work. Let us put some measurement noise plus 3 degrees, okay? 3 degrees of error in the sensors. Now, for each of the sensor, we have a cone. We don't have anymore a line, of course. And this is already 3 kilometers, because 2 or 3 kilometers, because of the distance. So it's useless. The information from one single sensor is useless. And now we have the green dots and the gray dots that are the two estimates with the proposed algorithm and with the, those are post-processing by all the vehicles. Okay, so that's the reason why it's plenty of green dots. Again, the only thing that I care of all this plot is this one. Percentage error of the naive solution, and here is the error of the proposed one. It's good. There is an improvement, something that I don't like, but there is clearly an improvement. Let's see how sensitive we are with respect to the noise by increasing to 6 degrees from each vehicle. Well, when I come to 6 degrees, without the simulation, it's always the same. Well, the two errors now are comparable. Okay, it means that I'm very sensitive to the noise, to the noise of the sensor. Okay, this is something I can solve. I can interact with the colleagues in charge on developing the sensor. But what can I do from the algorithmic aspect? Well, I can try to position the sensor in a way such that the data are richer. So now, if I position the sensor in that way, and of course I don't know where the thread is coming from, so it's a little bit tricky, this one. So now they are not all clusterized in a place, they are spread, and the target is coming here. The regressor has a much higher minimum singular value, is the condition number of the matrix, what we are looking for, basically, okay? And the estimate, always the green dots, now are much closer to the target with respect to the naive solution. So now it's very nice because here, from 15% dropping to 1-2%, even by increasing to 6 degrees, which was, I mean, dramatically low earlier, and dramatically high earlier, and now I'm keeping the error very small, the percentage error very small. So overall, if I want to see the norm of the error, is 100 meters with plus or minus 3 degrees for each sensor. So this is the presentation. This is a 4 years project with the Italian Navy. The first 2.5 elapsed. Actually, they are not consecutive, so it's a little bit tricky. We are going the water next month, and then we will the final demo, full scale is planned for next year, but it could be a little bit later, depending on the agenda of the Italian Navy. What is important is that we identified also the factors which influence the estimate, and basically, I mean, it's obvious, but the only one which affects with this kind of algorithms our error is the quality of the sensor. The communication, once we collect all the data, I mean, the communication is not affecting the error. The communication is affecting the delay that allow me to say, okay, I'm confident enough that there is a threat in this position. So it's very important from the overall objective of security, but it's not affecting the accuracy with which I give the solution. Another aspect that is very, very important is the configuration of the vehicle in the space. So how do I place my vehicle? If I have to keep security of the entrance of an harbor, is different if I have to keep security of a asset that is in the middle of the sea. Okay, because of course in one case the threat can arrive only from, let me say, half plane, you know, it can arrive from all the direction, but the entrance of the harbor is that, is 3 kilometers of segment. In another case, the threat can arrive from, all the plane. Planar situation, the third dimension does not affect, is decoupled. So we ignore it, but not because we are lazy, but because it doesn't affect. And the main problem is on the planar case. So we are not ignoring the depth because of a particular reason, but simply because it does not change the difficulty of the problem. Okay. I thank you for the attention. Of course, I thank all the colleagues from the 9 universities and the guys from the Italian Navy, which allowed us to work with them on that topic.
Thank you, Professor Antonelli. So we have some time for questions.
Hi, thank you for your talk. So I was wondering about how sensitive is your method to the localization accuracy of the individual assets? You mentioned the sensor accuracy, but not necessarily the position.
Okay, I was writing a proposal before my talk, and one line was to study the accuracy with respect to the vehicle localization. Yes, of course, we need to take into account and we need to quantify this. Of course, it is sensitive, but I don't know, I don't have a reply right now. I don't know how much it's sensitive.
All right, thanks.
Hi, thank you for the talk. How do you deal with, because you said that the hydrophones only had this PDF Gaussian noise, but in reality you have multi-path and stuff like that. Have you taken into account how to deal with those outliers?
For the measurement?
Yes.
Well, for the measurement, not yet. I mean, the measurement in that moment, our assumption is that we have a uniformly distributed PDF, which also, if I consider that we implemented a Z-inverse solution, is also something that is not correct. I mean, the Z-inverse is the optimal solution if the noise is Gaussian. So, see, this is something that we need to take into account also.
Okay, thank you.
I didn't understand.
So you're suggesting that as the sensors are close together, your accuracy is significantly lower. Can you quantify that, the accuracy change as a function of the distribution of the sensors?
Well, the measurement noise change as a function of the solution. Then the other, indirect function of the configuration of the vehicle is given by the numerical balance of the overall problem, because it changes the condition number of the regressor matrix. So basically, we can implement a mathematical optimization, and if we have only 2 vehicles, 2 sensors, the regressor is simply sinus minus cosinus, sinus minus cosinus, and we can compute in closed form the eigenvalues. So in this case, we can maximize it, okay? With the 6 vehicles, it's not closed form, but in post-processing, we compute the condition number. And what we have seen is that, in this case, if I have, those are 5, okay. If my thread comes in that direction, this is a really bad numerically balanced problem. And as a result, the estimation error is much higher with respect to this situation, where, I mean, this is not good as well, because they're very close to each other, but it's much better than this one. And in the end, the error is much smaller. Okay? It is a property of the matrix. But of course, from the engineering aspect, from the security aspect, I don't know where the target is coming from, because this is the target coming from the representation. And also, in a little bit more elaborated, here, I have 6 degrees of freedom of error for each of the sensors. Those are a little bit more clusterized. Let me say, it's not very, it's okay, but it could be better. And the error of, let me say, the proposed algorithm is similar to the, let me say, naive one. However, if with the same error, I have it in a different spatial configuration, and the only difference is the property of the matrix. This is the only difference between those two cases. Then now, my errors, this is one of the 6 generic data. It's the same for all. It's similar. And this is the...
Can you predict that for a particular configuration of the...
predict... okay, predict... okay. Yes and no, because the error in the Pson inverse, we know that is related to the condition number by some inequalities. And so those are, I mean, results of linear algebra. But in our case, there are a couple of assumptions made, and a couple of simplifications. So, and the noise is not Gaussian. So I'm not sure we can numerically predict it.
Okay, I think we'll close the questions. So thank you for the questions, and thank you, Professor Antonelli.